All right, let's get started here. First, you guys, things are going to get pretty real coming up. There's tests coming up. March, whatever it is. It's on the syllabus and it's in Canvas in the modules. I'm driving here this morning and I'm saying, keep my mouth shut, keep my mouth shut, keep my mouth shut. There it goes. But I can't. Please, 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 come into class. Get off your phones. You're not accomplishing anything. When I put that up there, please try that problem right away. And if you can't get the problem right away, oh, is there another one I can maybe be working on? If you cannot do these problems in seconds, you need to go to 426 to the tutoring lab on the 4th floor. We are going to have one 50-minute test coming up. 50 minutes. And if you hesitate at all, you are not going to get done with the test. So things are going to get real here in a hurry. Please, please, please evaluate your time, and maybe you might have to prioritize some things. I don't know. And if you do not come to class, I was really disappointed last night, and I can show you. I went into my YouTubes. And how many views? From last Wednesday, 3 views. 3. Now, I'm not sure if I should just quit recording and not post them. But you could at least, if you don't come to class and the YouTube videos are out there, you can put it on in the background, because you never know when I say in the recording somewhere, well, this is going to be on the test or something like that. If I'm going to make the effort to do all that, and if you're not going to come to class, which that's your prerogative, at least look at them on YouTube, right? So and I have reached, and I've been doing this for over 30 years. And I'll look at the test average and I'll drive away and I have windshield time. It's windshield time, windshield time. Was there a bad question? Did this or this or this? And usually, not usually, every single time, the answer is there's not a bad question. And I sat right in your chairs before. So please, 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 if you are dragging it all, I want you to succeed. For sure, for sure. I tell you, we need you people out in this world, for sure. Things are not going in the right direction in many, many areas, and we won't talk about that. But please, please, please. All right, that's enough of my rant. Let's get started here. Now, let's review this first, and then I'll ask for reviews on this. So, what is the oxidation state of the underlying ion? I'm hoping now that you can just do this. And we know that oxide, always, always, always like this, is -2 And you can say, well, that's -8. Hopefully you can say sodium's always +1. And this is a +7. And I will say this again, if you are hesitating on this, please spend some time. Here, you may have to look at silver. I'm not sure if you have silver memorized, probably not. I'm hoping you got that memorized, and for sure you should have -2 memorized on the oxides. AgClOO. -2, -2, +1. If you had to look it up, wouldn't take you too long. So that leaves us a +3, right? So we're looking at +7, +3. Now, this problem right here, if you are hesitating at all, please, I'm begging you, prioritize, try to work this out, go to 426. There is a tutor there from 8 a.m. to 3 p.m., especially on Friday. Nobody's going to be in there, right? And if you do go there and somebody's talking not chemistry and just kind of BSing and distracting you, you tell them to keep it down. This is for chemistry though, okay? All right, 2 moles. We need to get to hydrogen atoms. 1 mole. 6.022 times 10 to the 23rd. What's the term we need to put here? These are molecules, right? We would use the term molecules. These are non-metals bonded together. And then, oops, let me put in H2O. 1 molecule of H2O, 2 hydrogen atoms. Now, let's go to this learning topic. Let me show you something on here that we did previously. These problems right here that we did, that we solved out, you should be able to cover these up. And you don't have to punch these in your calculator again, but you need to do problems over and over and over so that there is no hesitation in your solution process. So you can cover this up and go 4.7 grams of potassium. And then, ooh, you can look it up on your periodic table, 1 mole. You know how to do that problem. You do not have to recalculate it, right? This is my technique of studying. Oop, yep, that one's done. It matches. I know how to do it. I'm going to go to the next one. Then I'm going to do all of these. And I'm going to do them over and over and over. So there is absolutely no hesitation. In the same way with the quiz. So I would do the quiz questions over and over and over. I would make sure you can do these over and over and over without hesitation. Use paper. Paper is cheap. So you got something like that, I might turn it sideways, do another one, do another one, do another one. This is done, I'm gonna throw it away. I'm gonna keep doing problems over and over so there's no hesitation. Okay. 1 through 22 here. What do we got for questions on this? Anybody got questions for me for 1 through 22? One through 22, 1 through 22. Which one? Which one?
17.
17. Let's see, 17. Oh, yes. All right, 17. A couple ways to do this. In order of increasing atomic mass. So we want the lightest one first, and we're going to go less than, or greater than, greater. I want less than, huh? Okay. So we have an atom of fluorine, and the atomic mass of fluorine is 19. Now that would be an AMU, correct? And one F2 molecule would be 2 of those. That would be 38 AMU. So we know that the atom obviously should be less mass than a molecule. So what you could do is, there's a couple ways. I would get everything in grams. So your units are all the same. So the conversion, 1 AMU to grams. And the same way up here, although you don't have to do that one. So this one's already in grams. You go AMU to grams, and here you can go 1 mole of fluorine to grams of fluorine. And then they would all match. So then you can compare your units to be all the same. Okay, anything else on this through 22? Yes.
Number 2.
Did you say 2? 2. Which of the following atoms are isotopes? So for isotopes, we need atoms of the same element. Oops, I can't spell same this morning. So the same element, and the same elements are barium here. So the only one that matches the same element is barium. So we have to have the same element, different numbers of neutrons, therefore different mass numbers. So this is the same element, barium, and the difference is this one has what? 3 more neutrons, right? 3 more neutrons. All right. Let's go here. I looked at chapter 3. I'm not seeing where chapter 3 is going to take as long as what's on the schedule, but maybe. Okay. So let's review what we did last time. We're only using 2 conversions here. 1 mole and then 2 Avogadro's number, depending upon what we're talking about. So it might be atoms. You know, an example would be sodium. If it's molecules, it's going to be nonmetals like this. If it's an ionic compound, NaCl. It doesn't matter, right? You can have 1 mole of pigs. You got 6.022 times 10 to the 23 pigs, right? Probably cover the earth a mile deep, but that's a lot of pigs. It's a big number. Otherwise, 1 mole of atoms, molecules, or ionic compound is equal to grams of that, right? And you're going to look at the periodic table to get this. So those are the only 2 conversions we are using. And remember, as we go forward, it always is 1 mole, right? Don't be changing that number. 1 mole, 1 mole, 1 mole. Just 1 mole. Okay. Then we looked at in percentage composition. And we said that we just are going to take the part over the whole and multiply by 100 and add the percent sign. So we did the percentage composition of aspirin, and for the last one, we just subtracted from 100. So if you have 2, if it's only like water, H2O, once you calculate 1 like this, and let's just say it's 60, the other one's 40, right? If you have 2, you don't have to do this for the other. Okay, then we said, what we're going to do is we're going to take this percentage composition data and we're going to come up with this actual formula of the compound. And before you get the entire molecular formula, what we have to solve for is the empirical formula. And we didn't do that. We didn't get to it. This is the steps we're going to do. So we left off. We need to do this one here. So we'll do this example here. So determine the empirical formula for iron oxide. So I put FeXOY. It is 34.97 grams of iron and 153.03 grams of oxide. Okay, step one, get grams. So we don't have to do anything. We've already got grams, right? So we can go right to step two. Step two, convert everything to moles. So we have 34.97 grams of iron. We know we're going to convert to moles. So I'm just going to set it up, and I'll grab my periodic table, but I'm going to set them both up. So grams of iron. $55.85. And oxygen, hopefully you start to remember 16.00. We know that grams are going to cancel out. And we're going to get moles. Grab a calculator. And we get 0.6261. Now, in the end, it wouldn't matter if you kept some sig figs here. They're not really sig figs. It wouldn't matter if you kept some extra numbers here. But let's just leave it at 4 here, and this would be mole of iron. And down here, we get 0.9394 molars, right? Okay. Now, switch color pens or pencil. Change. If you're doing this on the iPad with notably switch pen colors. Because the next step is to divide by the smallest, right? So the smallest out of this is 0.621, right? So I'm just going to change colors. Step 3, divide all moles by the smallest moles. 0.6261 and 0.6261. What does that produce? That produces 1 iron and 1.5 O's, right? So we get 1 and we get 1.5. So that gives us Fe1O 1.5. So that means we have to do step 4, right? We can't have 1.5, and step 4 says this, or if not whole number ratios, those are not whole number ratios. We need to make them whole number ratios. So in this case, we're going to multiply by 2. We multiply them both by 2. So we are finally going to get Fe2O3. How's that? Not bad, right? Fe2O3. Okay. Well, we better saddle up a bigger horse. Let's see what we got on the next page here. Okay. So on the next page, this is our empirical formula. We need to calculate the molecular formula. So we're given the empirical, we need to calculate the molecular. Now, what we are calculating here is we're calculating this multiplier here. We want to go from empirical to molecular. Empirical to molecular. What we're going to have to calculate is this multiplier. The book uses, I believe, an N in there. Different books use different things. So here's what we've got. So we have C4H9, and we need to calculate N, the multiplier, to get our molecular formula. Now, that multiplier N is always the molar mass. This N right here this N is equal to the molar mass, which should be, it's given, divided by the empirical formula mass. Now, the empirical formula mass is just this, right? That is our empirical formula. So in this case, what do we got here? We've got molar mass of 114.3 grams per mole. Divided by the empirical formula mass. So we're going to add up 4 carbons. What is carbon? 12.01. Hydrogen, 1.01. 12.01, 1.01. Grab your calculators. .13. Therefore, my multiplier is 2. You don't need it. This has to be a perfect whole number here. You don't need a calculator. Don't even grab your calculator. You know it's going to be a perfect whole number. So well, that's close enough to 2. So if I put 2 in there, gets me a final answer of C8H18. C8H18.
Is that reduced?
The empirical formula is the reduced form.
Oh,
Okay, so this is the true compound though. Yeah, so the molecular formula you can have. See, the empirical formula here is the same for both of these compounds. So this is the true molecular formula. All right, so back to that bigger horse. All right, using percentage composition, 24.3% carbon, 4.1% hydrogen. Ooh, the remaining percent is chlorine. The molar mass is 99. What is the molecular formula? Well, what percent has to be here? So we can go 100, right? There's 3 of them, so we could go 100. 71.6. 71.6. All right, so we get 71.6. And that would be percent. Okay. Step 1, get grams. Okay, what does percent mean? That means per 100, right? So what we're going to do is assume we have 100 grams of sample. So assume you've got 100 grams. If that's the case, out of 100 grams of sample, it would be 24.3 grams of carbon, 4.1 grams of hydrogen, and then 71.6 grams of chlorine. So if you have percent composition, just say, well, I'm just going to use 100 grams of sample. So we got grams. That's step 1. Step 2, convert everything to moles. So we're going to line these 3 up here. So don't write too big. We want to line all 3 up here. So we've got 24.3 grams of carbon. Now, if you have it memorized, let's just crank it in. We've got 12.01 grams of carbon, 1 mole of carbon. .1 grams of hydrogen. And 1.01 grams of hydrogen. 1 mole of hydrogen. And probably the last one, you got to look it up. 71.6 grams of chlorine. But hopefully you can just boom, 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 crank that out. I'm hoping. So 35.45 here, 35.45?
Yeah.
Okay. So 35.45. And then we know that you better be able to cancel these units, right? Oh, I'm missing my G. And again, it would not hurt to keep extra numbers in here, which I'm going to do. I'm going to keep a few extra numbers here. So here I would get, what do we get? 2.02. Yeah, 2.023. We're going to keep some extra numbers because we're going to divide by the smallest. And maybe it won't matter. And molar carbon. So what did I do? I did 4 decimal places. This is really going to be ugly in here. 4.0594.
Yep.
In here, 2.01975. The reason I kept some extra numbers is those, when you end up with a fraction and not a whole number, we want like 1.25, 1.33 to get those to come out to 2 decimal places. It doesn't hurt to keep an extra digit or 2. So that was step 2. Remember, step 1, just get grams. Step 2, get everything in moles. Step 3, divide by the smallest. So I'm going to switch colored pens, and my smallest is 2.01975. 2.01975. 2.01975 and 2.01975. I'm going to grab my calculator to see how close these come out to. So the first one, 1.00, that's perfect. So we get a 1 here, right? 1 for this one. Next one's a 2. So again, I used a couple extra digits in case we get really close to 1.33 or 1.25, but this one's a 2. And the last one is a 1. We don't even have to punch it in, right? So we have whole numbers, we're good. So our empirical formula is CH2Cl. And my N, I'm going to sneak in right here, I think. I'm going to go sideways here, N. My N is equal to my molar mass given 99 divided by my empirical formula mass. And remember, this should come out to be a whole number when you divide it. So if you get close to half of 99, if this looks anywhere near 50, I don't know what it is. It is near 50. So, and you've got the molar masses right over here. So we need 1 carbon, 2 hydrogen, 1 chlorine.
49.48.
49.48, okay. You got a little ugly on me there, 49.40, but I don't need a calculator now. That's 2, and that has to be a whole number. So. You know, that's 2. If that's 2, we end up with C2, H4, Cl2. Okay. All right. Let's look at this one. This is saddling up a bigger horse. This is saddling up a Clydesdale, I think. This is a big horse. Let's do this thing. Let's see what we got. In class, try this one. Okay, we'll try it. Determine the empirical and molecular formula of chrysotile asbestos. Chrysotile has the following percent composition. The molar mass is 520.8. So again, we are going to assume that we have 100 grams of sample. So we're going to change the percents to grams, 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 grams. And I guess I'll write them down in that order. So we got to convert grams to moles for step 2. So now we got that. We're just setting them up like this. And 1 mole of magnesium. 1 mole of silicon. So let's crank those through your calculator. And here again, you can keep a few extra digits. That's extra sig fig. I'll go an extra one yet, I think. And maybe 99 times out of 100, it's not going to matter. I just want to make sure if we get close to 1.33 or 1.25, we recognize it. Six. It kept going that way. I think those numbers are correct. Yes, they look pretty good. Okay, so now we are going to pick a different colored pen. We're going to divide by the smallest, right? And the smallest is 0.76896. So this should be 1.5. This is 1. That's what we get, right? So to even get our empirical formula here, we're going to have to multiply. So we got just enough room down below. So let's take all this down below. And down below, we're going to have our empirical formula is Mg 1.5 Si H 1.504. Right, we got double 1.5s. So to get our empirical formula, we of course are going to multiply by 2, right? And we got to multiply everything by 2. 1.5, there's a 1 right there, a 1.5 in the 4. We're multiplying everything by the same number. So we get an empirical formula of Mg3 Si2 H3O8. We still got to solve this baby for n. And n is going to equal to our molar mass given of 520.8. Over our empirical formula mass. 3 magnesiums, 2 silicons, 3 hydrogens, and an oxide. $260.13. 260.13. Okay. Again, this has to be a whole number. So this is looking beautiful. This is a 2. Okay. So then we are finally going to get an answer out of, if this is 2, our final answer is going to be Mg6Si4H6O16, huh? 64616, yes. Final answer. Okay, you should be able to finish up everything in OWL. Now, I would recommend that you do OWL, like, I moved the deadline, and maybe I shouldn't. I maybe should have kept it Sunday night. Try to get that OWL worked out, then you should be able to do, we only left 3 here. You should be able to do the last 3 on this. And this is due Tuesday next week. So if you got a final question on this, we can answer it Monday. So please, please, please work on everything, review everything, do problems over and over and over and over again, so that you are not hesitating. So come test time, when we got 24 problems to do and our time is up and you're done with 10. Please work on it. And if you got questions, stick around.